bonus lecture more about um, the application of spectrum methods into my own research. Um, and it deals with a special class of circuits that are relevant, let's say, for nanoscale resistances. And I'll try to um, give you a broad introduction to the subject. In order to do that, let me just describe first um, what are the main components in an electric circuit. There are two ports, in a sense, they have an entrance and an exit port, and are passive. These are, like in the slide, it's commonly the resistor. And suppose you apply a sinusoid of current, you will see, of course, a linear regime in which the resistance is proportional to the voltage, but also a nonlinear regime, but without hysteresis, let's say. Then you have the capacitor and the inductor, and from this perspective, they are very similar. If you look at the current voltage diagram, the response to a sinusoid is going to be an ellipse. And then what I want to discuss is the case of memristors, which are, if you want, something which resembles all the three components before, where they do have, when you have a response to sinusoids, both a hysteresis and this resistive behavior in which for a zero current, you're going to see zero voltage on the component. And for these reasons, you're going to have a pinch hysteresis loop. From the point of view of how you describe these components, in principle, they're not too hard to model. You are going to have an equation like the one in equation 1, which is basically the voltage is going to be proportional to the current, I. And you're going to have a proportionality constant, which here is called R of W, where now W is a parameter or several parameters that are in practice depend on time. Okay, and then you're going to have an equation of how the resistance depends on internal parameters. In general, you can have this internal parameter that we're going to call memory. It's going to depend either on current or on voltage as a function of time. But in principle, you can also have a decay factor like in equation 2, that plus or minus alpha. And if alpha is equal to 0, you say that basically this acts as a memory, because when you remove the applied voltage, the current is going to be 0. And then the system will remain in the state, resistive state, the state where it was when you switched it off. If alpha is non-zero or any other state that does not depend on the current voltage is non-zero, then you're going to have an drift at zero voltage or zero current. And in this case, you don't talk anymore about memristor, but memristive component. So the first interest, say, of the first paper that actually put memristors on the map in recent times was this one by Strukov, Williams, and collaborators. It's a major physics from 2008, where actually they described, they were looking at oxides of tungsten, the titanium dioxide, and they show that as a first approximation, this model is revised several times, but let's bring it up here because I'm going to discuss it. The voltage current relationship is the one they described in the previous slide, but then also they gave an explicit formula for the resistor, where they noticed that basically the resistor is going to be a convex sum of basically two limiting resistances, where the weighting factor is proportional to a parameter W, and W goes from 0 to D, or if you normalize it between in terms of 0, 1 component, basically you can remove the D from here, and the evolution of this parameter then is going to be basically proportional to the current. Okay, and like the third equation in this slide. And what they noticed was that the switching was between two order of magnitude. Basically, in the on case, which means when W in this equation is equal to 1, they observed 100 ohms. Meanwhile, when W is equal to 0, so in the switched case, they observed 16,000 ohms. So basically, uh, and this is also why they're called switches, is because in various phases of this dynamical system for a simple resistance, basically you're going to have a binary value for the resistance, either on or off. Okay, and this model describes very well the hysteresis I was mentioning before. The physical intuition is basically the following, and again, this model has been criticized, but in order to understand what's happening, it's good to know it. But basically, the idea is following: as the current passes through, the material gets doped, and the more doped it is, so that's why the D enters the equation. D is basically the amount of material that can be doped, um, or the length of the material. So the more doped it is, uh, the more uh, conductive the material is. And so in the doped phase, basically you're gonna have an on phase. In the undoped phase, you're gonna have a switched off phase, so a higher resistance. And basically you can think of this as a variable resistance where basically the internal parameter is given by the charge. So W, you can integrate the equation before and see that actually it's the charge. Um, and this was the first physical intuition behind these components. Of course, we are trivializing it. It should be said that this was not the first time that somebody observed this type of components. For years, Chua in 1971 had theorized these components, but until basically this paper by William Struckle and collaborators, people have not realized that certain materials behave as a memristor. Then honestly, people started to see memristors pretty much everywhere, and it became clear that several components that were thought to be variable resistance that could fit this paradigm of a new component. There are, in general, several reasons why people don't believe in memristors as a fundamental circuit component, and you can share these opinions or not. Um, uh, as a matter of fact, these exist, and you can see this behavior in several materials. So I'm not going to discuss that. So um, as a matter of fact, using a simple model is actually for me just a way to study the coherent behavior of certain materials that have several memristors in it. For instance, in the case of atomic switch networks, basically, if you want complex networks, as in very dense networks of silver ions. So you start from a seed, and you start the deposition of silver ions in material. This is going to build several filaments. These filaments in general behave exactly as simple memristor model. Um, and for instance, this paper by Avigenis and collaborators from 2012, where they observe and can image also these components, and they observed a disordered network structure for these materials. Also, they have several different behavior when you control them in AC and or in DC. When you apply uh, sinusoidal input to the system, you observe several subharmonics, meaning that there are non-linearities in the system, like in the figure here on the left. Meanwhile, when you apply a DC, so a constant voltage to this component, when you basically you observe a very slow relaxation and a 1 over F type of power spectrum, which is usually hints that there is some complex internal dynamics. So let's just give a hint of how a single memristor works by applying a very simple approach. So you start from a voltage, a voltage applied to the resistor, and so this has to satisfy equation 3. And also, we assume that the equation for the internal memory has to be like equation 4, and the resistance is the Williams-Struckle type, which is basically like in equation 5. Note that from here you can I use usually the opposite notation than Williams and Strukov. So for me, W is equal to 0 is basically in the on state, and W is equal to 1 is into the off state. You need to add to these three equations the fact that um, W's can cap up to at 1. So basically, you need to enforce that when you solve this differential equation, that W maximum is 1 and W minimum is 0. But otherwise, these three equations describe the dynamics of a memristor. And then suppose you apply a certain voltage T, then you can replace in the first equation the equation for the resistance, and then you obtain basically the last equation 6. And then if you define the flux at the integral of the voltage, this is basically circuit theory, then you can integrate the equation for the memristor and you obtain equation 7. Okay. In general, you can, this tells you how this is true if the memristors are controlled in a way in which they don't reach the boundaries of 0, 1, because you need to integrate, so in that phase, this is a continuous differential equation, but aside from this idea, or this effect, if you say for voltage which is a sinusoidal, the integral will be a cosine. And so in equation 7, where you see delta phi, you can replace the cosine, and this tells you that the internal memory actually responds as a cosine, square root of a cosine type of approach. So it's nonlinear. It has a nonlinear response. And what I'm interested in is actually not a single component, but it's a network of components. For that, you need to be a bit careful in the sense that when you apply, when you put these memristors into a network, you need to satisfy Kirchhoff's laws. And Kirchhoff's laws basically tells you that if you integrate the voltage on a loop for a residual component, basically this is going to be equal to the number of voltages which are voltage sources on that loop, like equation 8. Meanwhile, you can you can use the fact that the sum of currents, which is the first Kirchhoff law, sum of currents entering a node is equal to the sum number of currents, or the sum of the currents exiting that node, which is the conservation of charge, basically. And in terms of graph theory, you can actually express this in a very elegant manner via the following network decomposition that actually I'm pretty sure is going to be discussed also by Matteo Politini in his lecture. So I'm going to rather skip this, but the idea is the following. So you take if you have a graph, you can always do the following splitting. You take a tree, which a spanning tree in the graph, and then given this spanning tree, you can always divide the network in the edges that are in the tree and the edges that are not in the tree. And this is called 3-equal-3 splitting. If you have this splitting, then what you can do, you can actually express the resistances, or if you want, the voltages on the tree as a function of the voltages on the equal-tree. And the reason that you can do that is that because of the constraints on the network, not all currents or voltages are going to be independent. So, as a matter of fact, the number of independent degrees of freedom in the network, given the Kirchhoff's constraint, is reduced. And in terms of graph theory, you can actually express this in terms of trees splitting on the graph. So this implies, if you want, that like in the last equation of the slide, that some memories are going to be dependent on some other memories via some matrices that here I'm going to call Q. If this is true, then and in general, you can actually show that the amount of memory in a network is going to be less than actually the number of memories we apply in a network. For instance, if you have a network where there are 10 memory instances, but these are connected by and they have to satisfy the Kirchhoff's laws, and they are connected in a network. Then the number of independent memory instances is going to be proportional to the actual cardinality of the spanning tree. Because the cardinality of the spanning tree is equal, always equal to the number of nodes minus 1, that's actually the constraint amount of memory you can have in a network of memory instances that are connected and analog in the sense that they satisfy Kirchhoff's law. And in general, you can introduce this effective capacity for the network, which is the number of the cardinality of the spanning tree divided by the cardinality of the number of edges in the network. These ideas can be put in a formal sense, so in a formal way, and for a resistive network at equilibrium, there is always this um, solution which is given by equation 12. For the details on how this equation is derived, I suggest this paper at the bottom of this slide where we derive this equation. But all I want to say is that if you have starting from the equation 12 and inserting the knowledge of of um, the fact that these are memristors of the Struve-Williams type, then you can derive an effective differential equation for the network of memristors. Here I'm gonna go and describe in a second what these are. Let me mention here what R minus one is, which I forgot to mention in the previous slide. Let me go back about this. Let's see here. So R, which is defined implicitly in equation 5, is basically defined as R off minus R on divided by R on. If you go and look up how I do this equation, it's basically ratio. Okay, R minus 1 is basically R off minus R on divided by R on. And if you go and look at how this equation, so basically, in a sense, it describes the depth of how big the switching is for the memory store, and so it is a physical parameter. Okay. Now, if you go and look at and there is a typo in this equation, the R on should be set R on to 1 in this equation. But okay, let me just go and describe the second equation in this slide. So W is basically there are several typos in this slide. I'm really sorry about that. So W, where on the left hand side of this equation, is actually a vector. So imagine that you have vector with all the members in the network, and the dW and dt, this is the vector of all possible resistances in the network. The first term on the right hand side is again a vector, and alpha is basically represents the decay of each component to a certain state. In this case, if alpha is positive, by my convention, this will be R off. And the last term is basically a nonlinear network effect. The W in there is a diagonal matrix with, this is a bit of abusive notation. W is basically the diagonal matrix where the component memories are, and omega is where the network is contained, which basically is, and I'm going to use this now, it's a projector operator on the cycle of the graph, cycle space of the graph. So it's a purely network graph theory in origin, graph theoretic in origin. And basically I plus R minus 1 omega W is inverse, which is actually key here, is basically the nonlinear effect of the response of the network. And as a matter of fact, it's actually what makes this component very complicated. Okay, S here is the vector of a sources of voltage sources to each memristor. So you can have if you have n memristors, you can have n of these sources. So this is a vectorial equation in nature. Beta and alpha basically control the response of the network to or the memristors to decay. So when S is equal to 0, alpha is the memristor decay. When S is not 0, beta is how fast memristors usually respond to an applied voltage. So in this sense, all the complexity of the dynamics, if you want, is contained in this second equation, and it contains Kirchhoff's laws. So you can always simulate these for a simple class of memristors and actually have the Kirchhoff's laws satisfied. And the origin of omega, you can see it in this form. Take the equation we started from in the previous equation, okay? And R in this equation here is the diagonal matrix with the resistances, okay? In this case, if you set all the resistances to 1, you can see that the response of I, or the voltage, or the current, the solution of the currents to an applied voltage is like the last equation in equation 14, the rightmost equation, and basically omega comes from setting to 1 the resistance here, and you see from there the definition of the projector operator given the cycle matrix of the graph. Again, for details of how this equation is derived, I suggest there are some, if you're interested in this, there are some introductory papers at the end of this slide. But given this exact equation, then you can basically try to infer some properties of the dynamics of the memristors from this equation here. You can just simulate it and look at how the system behaves. Note that the nonlinearity is basically controlled by the ratio r-1 that usually in my papers I call psi. And for all these derivations are contained in this paper here, which is now published in PRE. All right, so let's just start and make some brutal approximations. So the first is, let's assume, and for this I should probably explain how the cycle matrix is defined. So the cycle matrix is basically the following matrix. You have L by M matrix. M is the number of edges, in this case memristors. L is the number of loops in the graph, fundamental loops in the graph. And you give an orientation to the loop and an orientation to the edges. So you basically get a directed graph. If the orientation of the loop is the same as the orientation of the edge, which is the current, then you are with a +1 there. If that loop does not have that edge contained in it, you put 0. If it is oriented in the opposite, it has the two loop, the voltage loop, the cycle loop, and the edge loop as the opposite orientation, you put a -1. So it is a matrix contained only on -1, 0, and 1. And the idea is, let's just look at generate, if you want, random graphs in this sense, and so generate -1, 0, and 1 a random, and basically see what happens. Okay. So once you have A, it's easy to calculate the projector operator because it's just defined in this form. Okay. Usually, you in order to realize to be consistent, you need to make sure that actually this is a real graph. So you need to make some extra assumptions. But let me skip these details from now. So for now, this is just a random matrix, okay, of size L by N. Then if you simulate the dynamical equation, you can see actually that you're gonna have in these averages, some memristors are gonna go to and hit the 1 state, and some memristors are gonna go and hit the 0, 1 state. If you go and look though at how the system responds in a certain sense, so you remove 1 from the blue curve, and you basically project it on the 0 state, and you plot it in log, you're gonna see that basically the system relaxes fairly slowly, okay, with a best fit exponent of a power law which is 0.93, and this is usually typical behavior observed in glassy materials. So this is also the reason of physical interest for this component. If you, for instance, go and look at what we said before about atomic speech networks, okay? In general, you will observe in 1 over f noise a power spectrum which is a power law, and it's 1 and the order of 1, let's say, in terms of the relaxation. And if you go and look at basically you have a certain relaxation for certain components, let's say e to the minus lambda t. If you take the sum, a certain distribution of these, which is pretty much what you observe in this slide. In this slide, you see several components that are relaxing with a certain time scale, but the sum of it, which is basically the red curve for those going to 0 and the blue curve for those going to 1, it's gonna actually follow a certain behavior. And if the relaxation, if the spectra of these lambdas basically is broad enough, then you're going to obtain a power law which is usually of order 1 in this sense. So since we obtain 0.93, the relaxation is going to be 0.93 plus 1. So it's going to be 1 order 1 point, the exponent of 1.93. And so this explains more or less what you observe in experiments, although it's not satisfactory. There are other things, but at least it gives the bulk of where you observe this power law relaxation or power spectra in this hard or um, very random networks of memristors. And a simple explanation can be observed like this. Okay, suppose you have a certain networks that behave like where the components are gonna hit with a certain time scale, linear time scale, 0. Okay, and you just look at the average of all of these. Each component is basically relaxes as CT, so it's linear relaxation. Okay, but you put a bunch of them. If you go and look at the average of all these relaxations, which is the curve in this behavior, you're gonna get a power law which is over the 1. So this is the phenomenon that we are describing. It's really like nothing more than what you're describing in this slide. And in realistic networks, though, the networks are non-random. For instance, in the experiments made by the group by Vizianis and collaborators, basically you see that usually these networks are not exactly um, so complex, but they follow, first they are two-dimensional, and they follow this fractal pattern, and usually these are called diffusion-limited aggregation networks. And the thing is, if you go and look at the realistic networks, you see actually they also follow some random relaxation. And in general, you need to explain why several networks have this property, why several networks, even if very different in nature, they have this power law relaxation. And something you can use is if you approximate the nonlinearity is small, so r minus 1 is close to 0, and you can solve this differential equation approximately, and you see that the behavior of the average memristor is basically an exponential, where the exponentially depends on the matrix VW in these equations. So VW here would be this VW would be this V here. Okay, so the spectra of V, and here it comes the spectral properties. The spectra of V are basically how broad your relaxation is. And you can show that actually that if the average, if you take this exponential, and the average is there is basically you can include the average on the spectra of V, then you're gonna get a 1/t relaxation, which is what we observe in simulations more or less. So it's the same order for the power law, and this is due to the fact that actually the spectra of this matrix, if it is random enough and broad enough, then it's gonna give you automatically, given an exponential relaxation, 1/t on average. And this can be explained when this is valid. It's actually, it depends on the number of loops you have in the graph. The more loops you have, which is basically the black curve here, so density of loop can be maximum 1. It is actually bounded by network constraint. But the more dense it is, the network, the more broad is actually the spectrum of this matrix V. And this is one reason why this is a combination of several effects. There are the random matrix. There's a random matrix component that we're using here, but also the fact the internal dynamics of these memristors in this approximation. So again, this is just a toy model that we're describing, and we are observing within this toy model an exact, let's say, I don't want to call it exact. It's an approximate exponent for the power law, which is of order 93, and versus the 1/t law that actually we can derive theoretically based only on graph theoretic and random matrix approach. And one open problem there is how we go from relaxation of memory to the zero relaxation for an effective resistance. And this is an area of research. Using the equation, in certain cases, you actually solve the network itself. I'm not going to discuss this. Actually, it came out in a paper, but it's describing this equation here, and I'm not going to go through. But you can actually, by an exact equation, solve in the network behavior of all memristors in this case, and you can actually look at within the limit of approximation whether you're reproducing certain behavior. And here I'm looking at exact versus numerical results, and so you see they actually match very well. If you increase the nonlinearity, they match less, but at least they follow the same pattern. And yeah, in the case of cosine, this looks like this. So omega bar, omega plus is actually the more Peirce inverse of the projector operator. So the conclusions, Memristors are, I find them interesting because of this. They have a combination of nonlinearities and Kirchhoff constraint. They introduce graph theory. There are complex relaxation phenomena, so it contains both statistical physics um, and graph theory in it, and nonlinear dynamical systems. They are appealing for various reasons. One is you can use them as memory, so you can use in this, some active area research and I work on. You can use them for computation, and you can apply a bunch of statistical physics machinery to them. There are plenty of open questions, so this is an invitation also for the students. And the last slide, I would like to introduce more or less the papers that where you can read about Memristors. I suggest, for instance, this paper here by Di Ventra and Traversa, which is a very recent on Journal of Applied Physics. And also, I did contribute to this field myself. Like it's me and Juan Pablo Carvajal wrote recently this review for the Journal of Technologies, and it's 40 plus pages with it's very introductory. Regarding the say if you, the graph theory approach, I recently wrote a paper with my student Anna Dregarac, and it recently came out in EPL. This is another perspective paper, but where we derived these all the questions that they describe in this paper in this presentation is in the paper here with Traversa and Di Ventra, the complex dynamics of memory circuits, and you can find it on the archive and on PRE. Otherwise, if you have any questions, please write to me. This is my email.